Find the open intervals on which the function is increasing or decreasing. The function is g of x equals the quantity x to the fourth plus 1 all over x squared. In order to find the derivative, so we can find the critical values that will help us find the intervals, we need to first use the quotient rule. Or at least that's how it looks. Because there's only one term in the denominator, this x squared, we can divide each term in the numerator by x squared to give us a new function that looks something like this. G of x equals x squared plus 1 over x squared. So now instead of using the quotient rule, the power rule can be used. So when you use the power rule to find the derivative, you get g prime of x equals 2x minus 2 over x to the third power. And we want to use this derivative so that we can find any critical values of our function. And what is key to remember is that critical values are where the derivative equals 0 and where the derivative is undefined. And because there's an x in the denominator, x cannot equal 0, which means g prime of x is undefined at x equals 0. So we have a critical value already at x equals 0. And when we actually go through and solve this equation for x, maybe we will get some other critical values. So in order to solve this equation for x, we need to multiply everything by x cubed to get rid of the denominator. And when you do that, the right side still stays 0. On the left side, the x cubed will cancel out in the second term, so that leaves us with a minus 2. And in the first term, we end up with 2x to the fourth power. The next thing we can do is add 2 to both sides and then divide both sides by 2 to get x to the fourth equaling 1. And what this tells us is that x equals plus or minus 1. So we have critical values plus and minus 1 and critical value x equal to 0. On this slide, I have the derivative from the previous slide, the critical values, and the critical values already mapped out on a number line. The critical values are what separate an interval from being increasing or decreasing. So in order for us to figure out which each interval is doing, we need to pick a test value. So I'm going to pick -2, that is less than -1. I'm going to pick 1/2 in here between -1 and 0. That's a -1/2. I'm going to pick a positive 1/2 over here. And to the right of 1, I'm going to pick a positive 2. In order for us to tell where the function is increasing or decreasing, we need to evaluate all of these test values in the derivative. G prime. So when we do this, if we get a value back that is positive, that means the original function is increasing on that interval. And if we get a value back that is negative, the original function will be decreasing on that interval. So when we evaluate the derivative, at negative 2, this is 2 times negative 2 minus 2 over negative 2 cubed, which is negative 4 plus 1/4, which is negative 3 3/4, which is less than 0. So since this gave us something that was less than 0, the function is decreasing between negative infinity and negative 1. So I'm going to start writing my answer down here. Decreasing from negative infinity to negative 1. And if you go through and you figure out all of these values, like we did down here, then you will see that when you evaluate the derivative at negative 1/2, you will get back something that is positive, which means that interval is increasing. So from negative 1 to 0, the original function is increasing. When you evaluate the derivative at 1/2, you will get something that is negative, which means that the original function is decreasing. So I have to union in another interval, 0, 1. And then the last value over here, 2, when you evaluate the derivative at 2, you will get back a positive number, which means the original function is increasing on that interval. So I'm going to come down here to the bottom and union in the other set 1 to infinity. So here are the intervals on which the original function is increasing or decreasing. The last part of this exercise is to find the relative extrema. And using the first derivative test, we know that if a function stops decreasing and starts increasing, that there will be a relative min at that x value. We also know that if the function stops increasing and starts decreasing, there should be a relative max at that x value. And over here at 1, there's another relative minimum. However, in the original function, there is a denominator of x squared, which means we have a vertical asymptote at x equals 0. That's right here. There cannot be a relative maximum at a vertical asymptote. So we just have two relative minimums for our function. And if you go through and find the y coordinate, you will find g of negative 1 to get the y coordinate. And that will give you back a positive 2. And if you substitute in positive 1 to get back a y coordinate, that will also give you a positive 2. So we have a relative minimum at negative 1, 2, and a relative minimum at positive 1, 2. Here are your relative extrema for the function g of x.